Okay, my clock says 1:35, so we'll get started. First off, I'm happy to answer any questions if people are having difficulty finding the resources for the class or following the class or logging in or anything like that. I know we've been virtual while we see how things go in the first few weeks of the semester, but I'm happy to have individual office hours, and I've chatted with a few of you all one-on-one, so I'm happy to keep doing that. And I have a couple more homeworks to grade. I'll give you some feedback, but we will have another homework assignment coming. I probably won't have it due for like a week and a half. I'll try and make it due on Monday, so you have some time to work on it. Not this coming Monday, the next Monday. I don't want to stack them up too much, but if you are comfortable with the first real assignment, homework number 2, we'll be in good shape. If you didn't like it or you really struggled with finding a good paper, let me know. But the assignments are really to help you find the stuff you're interested in. I had some really nice papers on SLS. I had some nice papers on Altem polyimides. There was a good one on recycling. There was another one on sustainability. And so the first round of homeworks was really good. I think people were finding good papers. And so I want to keep that up throughout the semester to make sure that everyone is looking for things that they want to read and then finding that connection between materials and additive and putting those things together. If you can hear me, putting those things together so you really understand how the details of polymers and the polymer science behind polymers and composites contributes to their performance and additives. So that's the theme of the class. And we're still on melt processing because there's a lot to talk about in melt processing, but we will get to SLA. We will get to SLS, which of course is a thermal process, but it's done differently. We will get to some other types of printing techniques like polyjet or material jetting. And so we'll cover a lot of different aspects of additive, but since material extrusion AM is so well known, especially from what we know about extrusion and injection molding, I want to cover that in detail to make those connections, and then we'll fill in other additive processes. So, we will still talk about thermal processing of polymers probably for the next week and a half or 2 weeks. We will keep talking about material extrusion AM, but it's really to cement this idea that you need to think about the characteristics of the material to make the AM work. And then to go further, I think lots of people are able to get reasonable performance out of ABS in material extrusion AM, but in order to get good performance out of Altem or out of PEEK or unknown materials, there's more work that has to be done. So you really want to keep in mind these fundamentals we've talked about polymers and how they might be applied to the process. And if you get sick of material extrusion AM, it's fine to let me know. We'll try and get on to some other stuff, and we'll go back and forth between materials. We're going to talk about composites today. Then we're going to go back to material extrusion. So we're going to try and alternate a little bit between talking details about materials and chemical structures and composites versus talking about AM processes. Is there any questions, anything that anyone wants to bring up before we go to slides and start talking about the lecture today? Okay, my chat is up, so feel free to stop me through the chat or ask questions, or you can unmute yourself and butt in. I think our Zoom lectures have been pretty okay. And of course, if you miss a class, the full Zoom lecture is on YouTube as well. And you're welcome to ask me questions or have office hours about any questions you might have after the lecture's over. So that's no problem. Okay, so let me share my screen here. Oh, that's not how I share my screen. Okay, that looks like it's sharing, and let me go over to the slides. All right, so if you all can see that and still hear me, we're in good shape for our lecture. And again, I'm looking at the chat, or you could just unmute yourself, ask me a question, whatever's comfortable. So now at this point, we've talked about a lot of the basics, and we're going to start talking about some details about specific materials. And so we'll go back to this polymer performance pyramid, or how different polymers have different requirements in terms of high glass transition temperature, semicrystalline versus amorphous, whether they're cheaper commodity plastics. And you know that sort of standard polymers, polyethylene, polypropylene, polystyrene, PVC, those are going to be cheap and easy to process. Whereas if you want things made out of polysulfone or polyimide or polyether imide, they're going to be more difficult to process and more expensive. And so this really forms or informs the polymer industry in terms of what polymers work for what applications, and why engineers and product designers choose different polymers for different applications. So in an airplane or in an autonomous aerial vehicle or a glider or something like that, people would really love to use polyethylene or polypropylene or polystyrene because it's cheap and easy. However, those are high strength applications, there's temperature requirements. And so you see a lot of the glider work and a lot of the aerospace work is done in polyimide, because those are the types of polymers that the industry has settled on in terms of having the performance, the fire retardance, the mechanical strength, the high temperature stability. And so people are just not choosing polymers because they usually have a detailed reason as to why they use polyphenylene oxide, or why they use ABS, or why they need a composite. So that's important to remember. And the polymer industry is huge, and we were talking about the processing window for all these different types of polymers. Well, let me first mention, of course, if you want to learn more about what's out there from companies that you can buy, you can go to DSM website or SABIC website or Arkema. We have some folks that are in end use industry in class, but I don't think we have anyone from a chemical company in class this round. So there are people that use polymers for applications, but then there's a huge industry that makes polymers. And so feel free to go to the various websites, both from additive manufacturing companies, because they sell materials, and also chemical companies or materials companies, because they sell feedstocks for additive. And there's a lot of information out there from manufacturers. And we talked about this idea of a processing window. And so how do you process different polymers? What are the relevant temperatures? If you buy some Ultem polyimide, how do you start thinking about processing that material? And so we really learn about processing windows from the current industry, which is extrusion, molding, compounding, etc. So as you start to investigate different materials and different things that you're interested in, don't forget to look at some of the traditional resources, all about molding, all about injection molding, all about rotomolding, because there's a lot of information already out there. And so the AM industry had to start somewhere. And so they started with some easy polymers to process, but now the additive manufacturing industry is really interested in bringing in new feedstocks. And so we have to look back at what we know already about these polymers and go from there. So that's just a recap of where we were before the holiday. Is there any question on this sort of idea of traditional polymers and where we find information from traditional extrusion industries or injection molding or extrusion? Any questions on that? Or is my message coming across in terms of polymers already exist in the wide world of materials. We just need to figure out how to use them for additive. All right, well, let's keep going. So that's just to remind you where we were. And so this is note set 2.5. This is on Box, and I'll continue to update the notes. So you want to check back on Box. I'll try and remind you when I can, but I'll update new material there. And so I don't think we saw one of these videos yet, but extrusion and injection molding is a huge industry, billions of dollars or hundreds of billions of dollars. And there's major manufacturing capability that basically makes everything that's a piece of plastic, from a cover for a remote control to a drone propeller to plastic dishes or plastic cups or even soda bottles and laundry bottles. There's just a tremendous industry that does extrusion and injection molding. And so you can check that out. This is a Wikipedia page here. And this serves as our reference for thinking about what's needed when we AM polymers. And we're going to talk today about the difference between extrusion and injection molding and material extrusion AM. So even though we call it material extrusion, you'll see that there are some big differences. So I'm going to show a couple videos because they're good. And I'll start the video and I'll stop it after it's past its useful lifetime. But there's some really nice resources on how this works in a general sense. And then we'll use this knowledge from extrusion and molding to think about AM. So let's switch over to YouTube. Let's see if this works. Let's start here. Okay, this is our first video right here. This is totally reasonable. And so we'll see if this comes through.
Now let's look at the inside of an extruder to see how it works. The plastic raw material in this hopper travels by gravity to the feed throat and drops onto the rotating screw. The rotation of the screw conveys the plastic forward through the heated barrel. As the plastic is conveyed forward along the screw, the channel depth decreases, forcing the plastic through a smaller area. The combination of compression and screw rotation causes friction, which generates heat. This is called shear heating.
Okay, so just to give you a scale, usually these extruders are 36 inches long, 60 inches long, 24 inches long. So they're a couple feet. And the screw size is an inch or 2 inch or 3 inch, something like that. So the scale of these extruders is usually much bigger than we're used to in terms of the scale of a material extrusion AM for a MakerBot or an Ultimaker or something like that. So keep in mind the scale and keep in mind this screw shearing as we go on.
This heat, along with the heat from the barrel heating system, melts the plastic. By the time the plastic is conveyed to the end of the screw, it should be well mixed and at a proper temperature and pressure needed by the die. The plastic is called a melt at this stage. Beyond the screw, there can be a screen pack. The screen pack is a set of wire mesh filters that the plastic must flow through. The screens are typically from 20 to 100 mesh, which indicates the wires per inch. The screen pack is supported by a breaker plate, which is a sturdy metal plate with many holes for the plastic to pass through. The screen pack filters contaminants from the melt. The screen pack must be set in place with a coarsest screen next to the breaker plate, so each screen can support a finer one. Otherwise, the pressure difference may break the fine wires, contaminating the product and possibly doing permanent damage to the die.
Okay, So that's just a very basic introduction to what's happening during extrusion. But basically, well, I closed it. But basically, we feed solid polymer into what's called the hopper, and then it goes through a shearing and melting, and there's things to balance the pressure, there's things to filter out contaminants. And then in one of those diagrams, you see what's called the die at the end, which is where the polymer comes out. So I'll use these terms like die, which is what shapes the polymer as it comes out. I'll use extrusion, and whether it's screw extrusion or whether it's material extrusion AM, we'll talk about the differences. And now this video is just a little bit more introduction, and this is a really interesting guy to listen to. He's a professor at University of Illinois, and this will give you an idea about all about injection molding. And we won't look at this whole video, but this will serve as a nice reference for you to think about where we're at.
Injection molding is the most common method for mass manufacturing plastic products. Examples include chairs, toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. Injection molding was invented to solve a problem for billiards. In the 19th century, billiard balls were composed of ivory harvested from the tusks of African elephants. This devastated the elephant population, so a billiards manufacturer offered a $10,000 prize for a replacement for ivory. And this spurred John Wesley Hyatt to develop one of the first plastics, celluloid, to create billiard balls. He patented an apparatus for molding products from celluloid. This apparatus was the birth of plastic injection molding. In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops a plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment called colorant, or with up to 15% recycled material, then fed into the injection molding machine. Before the mid-20th century, injection molding machines used only external heating of the barrel to melt the plastic before a plunger injected the molten material. But because plastic conducts heat poorly, the temperature was uneven in the barrel. Either the middle was too cool and not fully melted.
Okay, so this is a really important point, and we're going to talk about this in future slides. But you notice this early injection molding unit did not have a screw in the middle. And because plastic is a poor conductor of heat, you see this temperature differential from the outside of the filament or the outside of the barrel to the inside. And it turns out that this is a lot like AM, or at least traditional material extrusion AM now, where we have this temperature gradient in the filament. And so we'll discuss over the next couple lectures how polymers that go through this type of process give different properties than the polymers that go through a screw extrusion type of process. And so that's something important to remember, that this is relatively low shear because there is no screw extrusion. All right.
Or the outer regions were too hot and degraded the plastic. The solution was this: the reciprocating screw, often regarded as the most important contribution that revolutionized the plastics industry in the 20th century. In the earlier plunger-style machines, plastic filled completely the cylindrical barrel. But as I showed you, the plastic was not at a uniform temperature. The reciprocating screw overcomes this in three ways. First, in modern units, the plastic fills only the space around the shaft of the screw. This eliminates the cooler central region, leaving a thinner, evenly heated layer of plastic. Second, the screw has flights that wrap around the shaft. As the screw rotates, the flights transport the raw material forward through the barrel. The flights also serve to mix the plastic. The screw action agitates the melting pellets within the flights to create a uniform mixture. And third, the screw action itself heats the plastic throughout. The shaft's diameter increases along the screw so that the distance between the wall and the shaft decreases. The flights then squeeze out air as they move the plastic forward, and they shear the pellets and press them against the barrel's wall. This shearing creates friction and so heats the plastic throughout. This screw-induced shear supplies a majority of the heat needed to melt the plastic, between 60 and 90%, with the rest from the heater bands. The molten plastic flows past the front of the screw through indentations or flutes. When there's enough plastic to fill the mold at the front of the screw, it rams forward like a plunger, injecting the plastic into the mold. The plastic cannot flow backwards because when the screw pushes forward, a check ring is shoved against a thrust ring to block the backwards movement of the molten plastic. This forces the plastic into the mold. Initially, the cavity image is filled with air. As the molten plastic is injected, it forces air out of the mold, which escapes through vents. These vents are channels ground into the landing surface of the mold. They're very shallow, between 5 and 40 microns deep. The plastic, which has the consistency of warm honey, is too viscous to flow through the narrow vents. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath.
Okay, well, if you want to learn more about the molding part of injection molding, you're welcome to check that out. But anyway, now that we've seen a couple videos on screw extrusion and you're getting familiar with this idea of high shear, heat generation from the shear, squeezing out air in the pellets and the pellet feedstock itself, now we can contrast that, or we can cover a couple of key terms and then contrast that with what happens in traditional material extrusion AM. So the first definition that we really should think about is this idea of shear rate. So the shear rate is an engineering term, and it depends on the velocity and the distance. So in Couette flow, you can look up what Couette flow is, but basically this looks like this, and all shear processes can be decomposed to a geometry that's kind of like this, even though a screw is in cylindrical coordinates, and we're just going to use regular Cartesian coordinates here. But anyway, this is the idea that one plate is moving with a certain velocity, and there's a gap between the plates. So our polymer is in here, or our fluid. So this is a plate. This is a moving plate. And this right here is the polymer. Or fluid of any sort, because of course you can have a shear rate for any fluid. And so because the top plate is moving, it drags along the polymer with it because you have no slip boundary conditions at both boundaries. And so you get a velocity profile in the material, and you can calculate shear rate from this simple shear experiment. So this goes for all kinds of different shear geometries. Sometimes you have a cylinder in cylinder. So you have one cylinder. This is what Couette flow actually is. You have one cylinder rotating. You have another cylinder that's stationary. And then you have your polymer in the center right here that's being sheared. So this is what we might call cylindrical. Or cylinder and cylinder. And if you've ever used a Brookfield viscometer, this is the type of geometry that a Brookfield viscometer uses. But this idea of shear rate is important, and it tells us that the shear rate is higher when the velocity is higher, or the shear rate is higher when the gap is smaller. So if you try and force polymer through a very small gap, you can have high shear rates from that depending on the velocity. And of course, intuitively, if we increase the velocity, our shear rate will go up. And so these are important things to remember as we examine the shear rates that we encounter in AM, and the shear rates, how they might be different from traditional extrusion processing. So you just want to do a little studying on these terms and make sure you have an appreciation for that if you've never taken a fluids class. So that's shear rate. Also, as we start to talk about extrusion and look into processing windows for polymers, we're going to come across this term called melt strength. And that's been in some of the articles that you've read. And that will be an important concept when we talk about making a filament. We're going to have a couple lectures on filaments or rods. And so this is the modulus of molten polymer road. Or it's a measure of the extensional viscosity. So extensional viscosity just means you're extending the polymer. So it's like you're taking, you're squeezing a tube of toothpaste and you see the polymer drip down. And so let me turn on my camera here if I can figure this out. Okay, so if you can still hear me. And so the melt strength is you extrude polymer from a die. So this hand is the die. So it's molten polymer coming out. And this road right here, let's pretend my pen is the road. It's when this is molten and we pull on it, what's the modulus or what's the strength? So if we have very low melt strength, this thing will break because of gravity and it'll just drip, drip, drip out of the die and we won't have this nice continuous road. And so one of the things that we look for in terms of melt strength is, does this road hang together as we're doing our material extrusion AM? Because the head of our MakerBot or Ultimaker is going to be moving around. And so this road is going to have to stay intact. Otherwise, we're going to get breakage of the road. We're going to get defects. In a low melt strength polymer, it gets really hard to extrude in AM. And melt strength is really about what the molecular weight is and is related to the extensional viscosity of the material. So you can tune the melt strength by tuning the molecular weight. So that's important. Sometimes we do branching, long chain branching versus short chain branching, and you can read about it here. But if you come across a term like melt strength as you're reading about extrusion, this gives you a general introduction to what it is. And I shouldn't say that the melt strength, there's a value that we're looking for. The melt strength that you need, so let me write this down. So required melt strength depends on process characteristics. If you're printing very slow, you can print a polymer that has a lower melt strength. If you're printing very quickly, you probably need a polymer with higher melt strength because you're going to be pulling on that filament. But you'll see a lot of the terms that we talk about, people will ask, well, what's the best value or what's the right value to have? And what I'll always say is it depends on the process. It depends on your printing speed. It depends on the resolution that you want. In some cases, you're going to want very low viscosity and you're going to have very low melt strength because you're just trying to process a lot of material. So you're pushing a lot through the material extrusion AM process, and your resolution is going to suffer because of that. But that might be fine depending on the goals of what you're trying to do. Or you might be trying to do highly detailed work and printing very slowly and getting perfect resolution. And so you're going to want a higher melt strength, especially if you have a very small orifice where that road is going to have to hang together. So this just gives you a vocab word that you can think about in terms of characteristics of that molten filament. The other thing that we've talked about before, and we've seen this in previous slides, is this idea of melt flow index, or sometimes I think we saw it as a melt flow number, or something in terms of grams per minute or centimeters cubed per minute, something like that. So some units of amount versus time. And this basically gives us an idea of the flow of the polymer under a very specific set of conditions. So as opposed to a big rheology scan, something like this is a rheology scan where we're measuring the viscosity or modulus versus a large number of shear rates. Melt flow index is basically under one shear rate, under one set of conditions, how much polymer flows, how many grams, or how what's a volume. And so this is used as a QA, quality assurance or quality control in plastics production, because they don't want to measure the full rheology scan each and every time. They just need something simple to use. And they use something like this. So there's a couple different types of melt flow index tests, but they have an ASTM or an ISO number. So ISO is just a international standards organization, and ASTM used to stand for American Society of Testing Materials. Now it just is ASTM. There is no name that goes with it. But anyway, this is a melt flow index tester. If you work in an industrial plastics lab, they have one of these things. And basically, it's a calibrated mass. It's a heated barrel that works at a set temperature. It's got a standard die. And remember, the die is what the polymer is extruded through. And it usually has, whoops, a balance so you can get mass per time. So if you go to, say, an equipment company that sells equipment to ExxonMobil or Dow Chemical or Arkema, you can buy something called a melt flow index tester or something like that. But these are standard instruments because under a given set of conditions, under a given weight, under a given temperature, and under a given die, you'll get different melt flow indices depending on all of those things. And some polymers are measured under the same conditions all the time. Sometimes a grade of polymer or different grades of polymers will have different melt flow indices, perhaps at different temperatures. And so when we talk about grades of polymer, they usually have different additives. And different molecular weights. And also, along with molecular weights, and we haven't talked a lot about this, is different dispersities in molecular weight. This used to be called the polydispersity index, PDI. Now we just call it dispersity. But anyway, the breadth in the molecular weight distribution can tell us a lot about a polymer in addition to the molecular weight. And this is not a polymer science class, so we're not going to talk a lot about the dispersity of different polymers. But when you look at these different grades, sometimes you have a high melt flow grade, you have a low melt flow grade, you might have an injection molding grade, you might have a rotomolding grade, you might have an AM grade. Those are all different flavors of the same basic type of polymer. And so when you go on a website like MatWeb, or you go on ExxonMobil's website and you look at all the different polyethylenes that ExxonMobil sells, they might sell 100 different varieties of polyethylene, and they call those different grades. So this gets you oriented to some of the lingo, and they're generally, the grade is certified by something like the melt flow index or something like that. So that's some terminology for you. Any questions on this? I know we're getting into the weeds a little bit on extrusion and the basics of the polymer and plastics processing industry, but this forms the background for understanding AM. Any questions? All right, we'll keep going. And if anything occurs to you, I'm looking at the chat, etc. So just let me know. What's really interesting about injection molding specifically, and we just saw the video on injection molding, this is the cavity, and this is a 2D view. And so what happens, or it's a pseudo, let's say 2.5D. But what happens is, here is the injection of the polymer, and then the polymer flows to all these different parts. Because when you injection mold toothbrushes, you want to injection mold like 10 or 20 toothbrushes at a time. Or when you injection mold iPhone covers, you want to injection mold a bunch of parts at one time, because you saw how complicated injection molding is. And some of these injection molding machines can be like, it will inject 5 kilograms of polymer in one shot. So it's a lot of polymer, and it's a lot of space that they can fill in this mold. And so you can see all the different shear rates that are encountered in different parts of this mold. So shear rates from almost 10,000 reciprocal seconds all the way down to very low shear in the corner. So this is a dead end right here, as far away as you can get from the injection site, where you have very low shear rate. So the velocity is low, the part is wide at that point. And so if we look back at our expression for shear rate, as the shear rate goes down, the velocity is going down, the height is getting bigger, and so the shear rate gets very low in the corners of the mold, where the shear rate can be 10 or 20 times higher right at the injection site. So this is interesting because polymers need to be designed to withstand all these different shear rates. And you'll find for AM that we're generally under pretty low shear conditions. So AM operates here. And so that's really interesting, because polymers, the injection molding industry is huge. And so polymers have been designed to work over all these shear rates, but AM is going to work at very low shear rates. And we're going to study the shear rates in AM in a second. This is just to remind you that polymers have different viscosity or moduli as a function of shear rate, and we call this shear thinning. And we call it shear thinning because the viscosity or the modulus, they're the same thing, or we can convert between one or the other. The viscosity or shear rate, or the viscosity or modulus goes down as we go to higher and higher shear rate. And this is due to alignment. So viscosity decreases due to alignment of polymer chains. So that's just the physics of why you get shear thinning. And it turns out that a lot of non-Newtonian fluids shear thin that are macromolecular in nature. Some non-Newtonian fluids shear thicken, and we'll talk about that as well, because that's a problem. If you have a non-Newtonian fluid that gets more viscous as you try and shear it, that means it gets harder and harder to shear it as you're processing it. In this case, at these high shear rates, you might have a lower effective viscosity or modulus, and so that helps you process finer features, whereas in the low shear rate, the viscosity goes up and then the part holds its shape. So this is just something to remember, and we'll talk about the ramifications of this in AM. Okay, any questions? All right, we have a ways to go. This is a really interesting paper. I suggest you check this paper out and think about this. So this is hardcore engineering. You can see some equations right here in figure 1. That's about heat transfer. And if you've taken a heat transfer class, you know that this is called the Nusselt number or Nusselt number. We won't talk about that too much because I know not everyone in this class really wants a full fluid thermal transport part of this class, but this at least sets up the quantitative science and engineering that we can use to analyze our material extrusion AM, where we have our heated liquefier, we have our print nozzle, also called the die, and then we have our polymer melt, and of course we're feeding in solid feedstock. So we have to remember what our geometry is. And so this is just a cylinder that's tipped up on its side. And we're going to extrude. If I can get back to my, there we go. Extrude in this direction, and this is a plain barrel, so there's no screw. We'll look at some material extrusion AM processes that do have a screw extruder, like BAM has a screw extruder, so that's a little bit different situation, and you can analyze that using the traditional equations that we use to analyze injection molding or something like that, or you can take Professor Colby's polymer processing class. It's a MATSE 400 level class if you want to know all about screw extrusion. But this sets up a really easy relationship that we can think about in terms of heat transfer for melting this polymer. So we have how you heat polymer, right? How much heat is required. And then we have a cooling equation here, and we can put these together and come up with this idea of how to express the outlet temperature as a function of what's going on inside our heated liquefier. So we won't go through that. You can read the paper and think about that. But what's important in this is now we have the geometry of our heated liquefier that we can put some numbers around. So in traditional screw extrusion, I told you that the barrel length, so this thing, this is going to be like, let's say 36 inches. And the diameter of the barrel is something like 2 to 3 inches. And so this is a big process. It takes a while for polymer to get from the inlet to the outlet. And there's lots of shear, there's lots of time. So we have a long residence time, lots of shear. Oops. Lots of melting, et cetera, et cetera. We learned all about that. But in material extrusion AM, and this goes for everything other than processes like BAM or other sort of extrusion-driven processes. This is a short barrel. It's very small. The heated liquefier has small dimensions. And so we're interested in the heat transfer just in this small cylinder here where you have low shear and short residence time. And this goes for things like Stratasys. You know, a Fortis machine has this exact same heated liquefier. This goes for MakerBots, Ultimakers. Anything that's really filament fed has a heated liquefier that looks like this. Anything that's pellet fed is generally a screw extruder. So you just by looking at the AM machine, you can tell what kind of extrusion it is. So anyway, here are the dimensions. So you have your nozzle or your die, you have your heated liquefier dimensions, you have a heater block, etc. So this is the physical apparatus. And they characterized in this paper through both capillary rheometry and torsional rheometry. So torsional rheometry is two plates. One is moving, the other's not, and there's polymer in the middle. So this is something like a plate or a cone and plate rheometer. And a capillary rheometer is a capillary that extrudes filament. So capillary rheometer is very close to what we have in material extrusion AM, where a cone and plate rheometer or a plate and plate rheometer is a traditional rheometry geometry, but you see that they have very similar results in terms of viscosity, as a function of shear rate here. And this angular frequency is just a measurement of the what's happening in the rheometer. But this is nice characterization of the material. I think the polymer that they use is PLA. They have a reference temperature there and everything else. That's very nice. And then the last slide that we'll talk about in this paper is that they look at the pressure versus apparent shear rate in heated liquefier. So they're talking about how much pressure you need to exert on the raw material in order to get a certain apparent shear rate, or that relates to how much polymer is extruded. Oops, extruded. as well as the power that's needed in order to get a certain 3D printer speed setting. So this speed setting is how fast can you print? And it's in terms of, well, it will be in terms of centimeters per second, or sometimes you see meters a minute, or some sort of speed that you set in the software. So how fast can you move the heated liquefier and still keep all the roads organized? So you need good melt strength as you go to high speed, versus how much power you need in order to print that material at a given speed. And so there's a lot of details in there about the heat transfer. There's a lot of details in there about how much pressure you need as a function of the printer setting. And here's the heated liquefier temperatures right here. So you can see that you can bring the pressure down if you go to higher temperature, but you're also encountering higher shear rates. And so that's going to change your viscosity. And you can see apparent shear rates here between 2000 inverse seconds and 500 inverse seconds. And so that shows you that you're printing, you know, out here, right, in terms of what the rheology shows us. But this starts to put together some printer parameters, material characteristics, and then engineering analysis of the print process. And this is for, again, material extrusion AM. And we're not going to go through this paper in detail anymore. I'm actually going to assign it for an upcoming homework assignment. And so if you want to read more about this paper right here, you'll be able to, and there will be a couple other papers that you can read instead. So I'm not going to force everyone to read this, but this gets to now the rheology. It's in the Journal of Rheology. What is the polymer doing under material extrusion AM conditions that might be different than what the polymer is experiencing in one of these screw extrusion type processes? So I know that's a lot of technical detail, especially if you haven't taken a thermal fluids class before, but I'd be happy to answer any questions, or we can talk in detail about any of the data. Or once you read this paper, when you're doing your homework, you're welcome to ask more questions about how they're discussing certain things, or how they're connecting the material characteristics to the printer characteristics. But this gets to now, how do you co-design a material and a printing process, and how do you work through some of these details for whatever sort of polymer processing you're interested in. And we'll look at similar papers for SLS, for vat photopolymerization. There's not a lot of papers like this for material jetting, but we'll talk about some of these details where we can get key information that we can put into a model, or to use to do process planning or something like that, and take AM further with these materials. Okay, we'll pause here for a second if anyone has any questions.
Dr. Hickner.
Yeah, go ahead.
So what's the benefit of a twin extruder? Is it just higher shear rate?
That is a very good question. We're going to talk about twin screw. So it's usually called a twin screw extruder. And you get higher shear with the twin screw. So this is usually single screw. Extrusion versus twin screw And so you get higher shear with these two screws, and you get more mixing. So you get higher shear, and you get more mixing. So when you go to make composites, or when you go to compound polymers or mix polymers together with additives or colorants, or what we saw in that video, that's generally done in a compounding extruder or a twin screw extruder, but they're much more expensive. They can cause bigger changes in the material. And so we'll talk about that in a second, but usually for routine injection molding, we do single screw extrusion, where we're not trying to get two different materials to mix together. But we're going to talk about twin screw extrusion in the next set of slides here. Good question.
Thank you. Thank you.
Other questions? And I think there's some really awesome twin screw extrusion demos on YouTube. I'll try and find one, but they show some really nice mixing simulations and show you how fast that these twin screw extruders can mix two fluids together. So that's interesting. All right, so you got a preview of where we're headed in terms of the details of material extrusion AM. We're gonna back up a little bit, and we're going to talk about details of materials. So this is lecture slide 3, or lecture 3, and it's just numbered as they're put together. And this is in Box. If you can't find it, sometimes you need to relog into Box. And so this is with the other notes. And so we're going to talk about different materials, different polymers, and their composites. So we're going to talk about some of the key polymers and composites. Then we're going to go back and talk about material extrusion AM in a little bit more detail. But I wanted to take a break from Nusselt numbers and heat transfer and talk about chemistry and different polymers that are out there. So there's lots of different types of polymers available. So everything on the polymer performance pyramid, and these are some of the other types of materials that you should be familiar with. So whether it's PEEK or PEC, whether it's polyphenol sulfone or polyacetal or ultem polyether imide, you know, there's a lot of, let's say, brand names like ultem. There's a lot of technical names like polyether imide. And then, of course, there's chemical structure. I won't draw the chemical structure of ultem, but you can look it up. And of course, there's the abbreviation. So PEI generally stands for polyether imide, but you'll notice we run out of letters pretty quickly for all the different polymers. So you have to sometimes be on your toes about whether they're talking about polyether imide or polyethylene imine. They're both abbreviated PEI, and so you'll have to use your context clues to figure out what they're talking about. Okay, so nylons are aliphatic polyamides. This is nylon 12, and this is different than nylon 6 and nylon 6,6. And so nylon 12 is really interesting because you notice it's got something that looks like polyethylene, but it's got the amide group right here. So it's an amide. And we know that amides have hydrogen bonding. But the reason that PA12 and PA11 are used a lot in SLS is because they have properties that are between our usual aliphatic nylons, nylon 6 and nylon 6,6, and polyolefins. So we get good melting characteristics of this aliphatic polyimide, but the melt viscosity is not so high that you can get good fusion, or this has a reasonable surface tension. And we'll talk about that when we talk about SLS. So this is just to introduce you to what PA12 is. And of course, PA11 is just one carbon shorter, because this is, there's 12 carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Don't forget, in nylons, the carbonyl carbon is counted as part of the nomenclature. And so PA11 is going to have 11 carbons. And then nylon 6 and nylon 6,6 are two different polymers made by different routes. One is made by polycondensation and one is made by ring opening polymerization. You can look at those when you take a polymer science course. But this is one interesting example where the property of the material was tuned specifically to promote AM, and in this case, SLS. And we'll talk more about nylons when we get to SLS, because there's a lot done in them.
I have a quick question.
Go ahead.
For the nylon 6 versus nylon 6,6, do they both have a 6 carbon backbone? And it's just the fact that they're made differently that is there difference, or is it?
Yeah, so if
there more going on there?
There's more going on there. So nylon 6 is made from ring opening polymerization of lactam. And so what happens in that ring opening polymerization is you have an amide bond, then you have 6 carbons, and then you have another amide bond and another, 5 carbons, because it's nylon 6. So nylon 6 looks exactly like nylon 12, just shorter.
Right.
What happens with nylon 6,6, this is made by polycondensation of a diamine and a diacid, and so you have a different order of the amide bond depending on where you are in the chain. So it's nitrogen, carbons, and then nitrogen, and then carbons. And so the microstructure is different than nylon 6. So every polyamide with one number looks like this. Every polyamide with 2 numbers specifies a diamine plus diacid. And this is not, this is not a polymer chemistry course. So you can look up the chemical structure of nylon 6 and look up the chemical structure of nylon 6,6, or sometimes they make nylon 6,8. Sometimes they make nylon 4,10. And that tells you now you have 2 different carbon chains that you can optimize. So single number, these are single number nylons. And nylon is actually a brand name. Polyamides, of course, are what we're interested in. But single number nylons are all this structure, just with longer or shorter polyethylene-like chains. But all double number nylons, nylon 610, nylon 810, nylon 410, nylon 6,6, are all naming the number of carbons in the diamine and then the number of carbons in the diacid. And so look up those 2 chemical structures. And if you don't sort of understand how those molecules are put together, I'd be happy to do some office hours, or we can talk about that next class.
Okay, awesome. Yeah. Thank you.
Yeah, that's just in the weeds a little bit on polyamides, but it's good to understand where they come from. And as you change this distance, so as you change the number of carbons, you change the processing of the polymer because of this amide hydrogen bonding. So when you have more hydrogen bonding, the material is stiffer and harder to process. When you have less hydrogen bonding, the material is not as stiff and easier to process. So that's what industry does in terms of tuning the polymer properties in order to make it work in whatever process they're interested in.
Very cool.
All right.
Okay. Awesome. Thank you.
Yep, all about nylons. And there's tons of nylons, there's tons of grades of nylons out there. So check it out if you're interested in using polyamides in your process. Polyacetal and polyoxymethylene are exactly the same thing, and they look like this. And so if you go to a machine shop, this is a really nice polymer to machine. However, it's not very oxidatively stable because it's an aliphatic polyether. And so it's got high strength, it's got good hardness, it's pretty rigid. They like to, the machinists like to machine it because it behaves well. It's a semi-crystalline polymer, but it's susceptible to polymer degradation because of its structure. So you won't see a lot of additive of polyacetal or polyoxymethylene. You'll see them both. But this is an interesting polymer to think about in terms of what materials should be in the additive literature. What materials do we want to learn about? And so I know that people are working on SLS of this, and also this will work in material extrusion AM. And so this is something to consider as you're looking through the polymers and thinking about what materials you might be interested in for various aspects of AM. So this one is less well known, but there's lots of molding grades of this material. You can find out a lot about polyoxymethylene in the injection molding industry. So it's a polymer that you should have sort of in your database. These are two different types of polyimides. One is Altem and one is Kapton. These are both polyimides. So if you work in a clean room, you see lots of Kapton tape, or you see the brown transparent tape. Or if you take apart your desktop printer, like your HP PhotoSmart printer, there's the brown material on the print head, or sometimes there's a ribbon that looks brown with wires in it. That's all Kapton. And so this is insoluble. And so it's mostly just used as film. So insoluble polymer. And it's mostly used as film or tape or something like that. Whereas Altem polyimide is thermoplastic. And so if you get something machined at the machine shop and you have a block of polyimide that you buy from McMaster Carr, it's usually Altem or a grade of Altem. You can't get a block of Kapton. It's not supplied that way. But this is a high temperature material. It's easy to machine. It's expensive. It's a little bit brown because this imide bond right here gives it that brown tinge. And so this is used a lot in aerospace because it's high temperature. This is also amorphous. High TG. And it's formulated for use in aerospace. It's very stiff. It's low flammability, all the stuff that we need for high performance materials in aerospace. However, Altem is not used in automotive very often because it's too expensive. So there are other plastics like nylons, like polyurethanes, like ABS, that when used as composites, you can get some of the stiffness of Altem, but not necessarily the high temperature resistance. And for a lot of automotive applications, it turns out that you don't need super high temperature resistance like you need in aerospace. And of course, you know, if something breaks in a car, it's, you know, an inconvenience. If something breaks in an airplane, that's a much bigger problem because there's no shoulder to pull over to when you're 30,000 feet up in the air. And so sometimes for critical applications, the material is overspec'd, whereas for automotive, they're selling consumer products. And of course, the first thing that people think about when they think about cars is what color is it, how fast does it go, and how much does it cost? And so cost is right up there for automotive, and cost is certainly an issue in aerospace, but it's not one of the top things that people think about. So anyway, polyimides are the general class, or polyether imides are the general class of materials. And you've seen probably both of these types of polyether imides. One is in film, the other is in high-tech parts. So remember those polymers. And this is just a synthesis of Kapton. This is and so it undergoes this insoluble thermal imidization. And so that's just interesting. If I could write Kapton in a way that you could read it. So if you're interested in polymer synthesis, that's an interesting example. So polycarbonate is an important polymer, and this is bisphenol A polycarbonate. So you remember all the uproar about bisphenol A. This is the polymer that they used to make Nalgene bottles out of, and baby bottles and everything else. And it contains this bisphenol A residue in there. Does anyone know what they changed to? So you used to be able to buy a big Nalgene bottle that was polycarbonate. Has anyone bought a drink bottle lately and seen what plastic they use on it, or what brand name they use on like a refillable water bottle if it's not metal? So you see things called Triton. And so if you go to Target or Appalachian Outdoors or REI or whatever, you see things called Triton bottles. And so these are the big clear plastic refillable water bottles, and Triton is a polyester. It's like PET, but it's not PET because there's another comonomer in there to change the crystallinity and increase the impact resistance of PET. And so this is what they use now instead of polycarbonate because of bisphenol A. But anyway, polycarbonate's still out there. It's used in applications where you need good impact resistance. Of course, it's also used in applications where you need very clear or optical quality components, but that's hard to get in AM. We'll talk about that if we have time. But polycarbonate's still a tough material, and that's the structure of bisphenol A polycarbonate. Here's polyphenyl sulfone and polyether sulfone. These are just different flavors of polysulfones. And so these polymers are generally less temperature resistant than Ultem, but cheaper and easier to process. And so when you start designing a component out of plastic, you might start off with, okay, can I make it out of polyethylene or polypropylene? No. Okay, maybe I should make it out of polyacetal. Maybe not. Maybe I need to make it out of nylon. So I'm climbing up the polymer pyramid, looking for the right properties, the right cost, that optimization of performance versus what it's going to take to make that part. Okay, maybe I should make it out of polycarbonate or polysulfone. No, maybe it needs to be Ultem. Now you're really climbing up in terms of cost, and finally you get to something like PEEK or polyaryline ether ketones. And so we'll talk about all different flavors of PEEK next time because we're out of time. But this few series of slides sort of gives you an idea of what it takes to climb up that polymer pyramid, some of the different chemical structures involved, and then it's all about finding the right material for the right application and how we might process that in our material extrusion AM. So we'll continue talking about polymers, especially high temperature polymers. We'll talk a little bit about composites, and then we'll go back and we'll talk about some of the details, again, of material extrusion AM. So we'll go back and forth between process and materials, and we'll continue building up this story for material extrusion AM for a couple more lectures. Any questions? All right, well, I'm available for office hours or chatting anytime. You can expect another homework to pop up here soon, and I'll get you, there's about 5 or 6 homeworks I still need to grade. I'll get you that today so you have something to go on for the next assignment. So thank you very much, and I will see you on Zoom on Thursday. Thanks a lot.
Thank you.
Thanks.
Thank you. See ya.
Thank you.